Hello everyone, so today we will delve into evolutionary algorithms and we will discuss how to implement different methods. And last time we talked about evolutionary algorithms as population-based method with very specific steps for uh, generation and selection, and today we will pay a closer attention to these aspects. So first, of course, let's briefly discuss what were the components of evolutionary algorithms, or in general, what components are in evolutionary algorithms. So we have the general scheme. So we, of course, first initialize a population of candidate solutions, and we evaluate them. Then we have a loop in which we have three steps. First is generating new solutions, candidate solutions, by applying mutation and recombination to our current population. Then we evaluate all new solutions, and in the end we select a new population from the last one, the old one, and new candidates, new individuals. And now I want to highlight the following things. First, we have mutation and recombination. So these two operations we need to specify somehow for a given representation. Then we need to evaluate. So we need to define what is our fitness function. And as we'll see in a second, of course, it should be somehow connected with the objective function, but we can modify it, let's say, on the fly. So that's why it will be not necessarily one-to-one mapping between objective function and fitness function. And then in the end, we'll talk how to select a new population. So let's start with fitness function, because this is something like we should always start with, right? So we have an optimization problem. We need to specify what is the objective function. So here we should first discuss what is the fitness function. So the fitness function, I will repeat it, I think, forever, so that you will remember. So the fitness function corresponds to the objective function, right? However, it could be modified to improve the searching process or this optimization process. And what are common issues in evolutionary algorithms? So first of all is dominance. So some individuals, they surpass all other individuals. All right. So what does it mean? It means that our algorithm will find a solution that is good or very good. However, this is still a local optimum. And then it will attract all other individuals to follow this direction, right? So then, of course, exploration is very bad. Another potential issue is crowding. Because it could be again that some individuals they attract all others to some region. And then the search becomes very dense in this region, all right? And so that's why, again, it becomes this exploitation mode in some sense. Also, maybe one additional comment on dominance. So as we will see, or in general, it could be that the selection mechanism could be very biased towards one individual. And then, of course, all these mechanisms could work improperly. And another potential issue is the vanishing selective pressure. What does it mean? It means that when we have fitness functions, fitness values, and differences between fitness values are really small, so then selecting any point is like uniform. So then the selection may be very bad. It could behave almost like a uniform random sampling that we discussed previously, 2 lectures before. So it means that instead of following good directions in the search space, we are almost like sampling at random. And so how we can somehow alleviate these issues. So there are different techniques. I will briefly discuss some of them, and if you want to look further into this, so I suggest please take a look at some textbooks, Gusti's book, or others. And the first possible solution is to use something which is called linear dynamic scaling. What does it mean? So it means that we scale our original objective function with some hyperparameter alpha that is non-negative, or actually positive, and then we subtract minimum or minimal value of the fitness function of points in our current population. All right. So as you can see, so then we will have this. If a lot of values are similar, so then by subtracting this minimum, there is at least this chance that these differences will become larger. Okay. So some points will be very low, but some others it will be larger. Or if there is some there are something like values that are very different, so again we can somehow modulate it because also we have this alpha hyperparameter. Another technique, it's sigma scaling, and the idea is that we calculate the mean value of the population, it's mu t, and we also calculate the variance of the population. All right. So now what we do, we just, in some sense, we rescale everything. So first of all, we subtract the mean value. So now we will have, everything is shifted, and then we'll also subtract the variance that is scaled. Okay. And now again we hope that it will help us with having bigger differences between points and so on, right? So to differentiate between points. So as you can see, so why we should think about this fitness function that is related to the objective, maybe only, is that actually this linear dynamic scaling or sigma scaling, these fitness functions, they consist of change objective function, for instance. All right. So now, as I said, so if you are interested more into this topic, so I suggest to go into any textbook on evolutionary computing. Because then these are not so widely used. I think it's for maybe some more specific cases, for some specific optimization, it's useful. All right. So now selection mechanism. I believe that these are very important, and again, it's very good to know what kind of selection mechanism we can use, and we will distinguish deterministic and stochastic selection mechanism. So deterministic, of course, it will be always applied in the same way. Like for instance, in local search, we just pick the better point. And in stochastic selection, there is a randomness involved. So in, like for instance, in the Metropolis Hastings algorithm, we can get a better point, but still we look at how, in some sense, how better is this, and we will randomly select it. If it's much better, then there is higher probability that it will be selected. And also we will distinguish two categories of selection mechanisms. So parent selection, so for instance, for recombination and mutation, we can select which parents, so which candidate solution, which individuals from the old population are used to modify or generate new individuals. And survivor selection, so this is the main step. So this is this big step select in these algorithms, and this determines what is the next population. And of course, maybe another remark, some of selection mechanisms could be used both for parent and survivor selection. So what is what are possible parent selection mechanisms? So the simplest case is to just randomly select 2 points, right? So it could be very often it works very well, right? So this is a randomness that we introduce, but also so it doesn't favor any point, right? So you can say if we want to maybe explore a little bit more, so that we can allow to get a bit different directions, then of course by exploring more we need to evaluate more data points, right? Another selection mechanism is proportional selection, and this is the idea that we sample parents by normalizing fitness values, right? So it should give us a little bit, so it will be never that the best point is always selected. It will be more like we will assign some probabilities to different points, and not necessarily the strongest points will always be selected, right? And we can do it in 2 ways. We can do it with exponential function, and then of course we have a negative value of objective function, fitness function, or we can calculate it by just normalizing fitness functions. However, then in this case we assume the maximization task. Potential issues, so dominance. So the problem is that we can select too often the strongest points. And another thing, if we use this just normalization of the fitness function, we can have problems with translations. So if we add, for instance, to all fitness values some quantity, like, I don't know, let's say we add to all 5, so then these probabilities will change. However, this is not the case if we use exponential function, all right? Because this is the exponent, it will cancel out. Actually, maybe we can quickly look into this, so we can quickly calculate something. Do we have it? Yes. So let's say that we have 5, 3, and 2. If we do now f divided by f, maybe go a little bit here. If we have fi divided by sum, right? So we have 5 divided by 10, 0.5. Now we have 3 divided by 10 and 2 divided by 10. The problem is that if we add now, let's say we'll add 5 to all these values. We added 5. So now if we again apply this formula, so we will have 15 divided by 20, 8 divided by 20, 7 divided by, oh, do I calculate correctly? It's incorrect. So we have 15, and so this is, and this is not 15, but this is 10. Or maybe I can erase it. Right. Yeah, all right. Again, brush, all right. So we have 10 divided by 25. We have 8 divided by 25, 7 divided by 25. So here we have, of course, 0.3, here we have 0.2. But now, here we have 0.4, here we have 0.32, and here we have 0.28. And now you see that these values are totally different. However, if we now do, now if we do it with exponent, right? So now we will see that actually if we add e to the power of 5 plus a, whatever it is, because it's the property of exponent, is equivalent to that. So now we are able to actually add everywhere here e to the power of a, and it will be the same here, e to the power of a, and we cancel out. So now we see that actually with exponent this is not the case anymore. All right. And now maybe, just in case, we'll open if we need to calculate something again. Now we can come back to the presentation. All right. So yeah, we see that actually with this proportional selection, the dominance issue is still there if we use exponential function, but exponent, but at least this is invariant translation. All right. So another thing is something that is called ranking selection. So in order to avoid this problem with dominance and to be invariant to magnitude of the fitness value, people propose to use ranking. First idea is the linear ranking selection. So first is the worst individual, and the last one is the best one. Then if we use some hyperparameter S that is between 1 and 2, so then we can calculate these probabilities in the following way. So then we see there's this 2 minus S divided by the size of the population plus 2 times the ranking of an individual times S minus 1 divided by, and we see this is dependent on, the denominator is dependent on the size of the population. You can please check at home, maybe please write down a simple code or use Excel sheet or whatever to calculate that when you sort individuals in an ascending order, so then you can indeed have very nice probabilities, and because this is only dependent on ranking, so you will never be dependent on the value of individuals. So then there is always the same probability for selecting individuals at a given rank. Another possible ranking scheme is exponential ranking selection. So we sort first all points, and then we just take exponent of the place, and this will give us again the same probabilities. But in this case, of course, it will be that we encourage rather this best points, which is also not maybe very good. How to implement these selection mechanisms? There are different approaches. One approach is to use the roulette wheel. So now we see that we assign like this pie chart. We assign pieces of this chart to different individuals. Here we have 1, 2, 3, 4, 5, 6 individuals, and then we implemented that we just roll this roulette wheel, and where is the pointer then we pick this individual, right? So for instance, let's say we pick the blue one or green one or whatever. Another possible implementation is the tournament selection. So we pick k individuals randomly, with or without replacement. Then they play a tournament. So we check. We check which of these individuals win most often. So what does it mean that they win? We check their fitness values, and if an individual has higher fitness functions function than the other, so then we say that it wins. And after playing these games, let's say between each other, or among each other, so then we just pick the best individual and add it to matching pool, and then we repeat. And after some repetitions, we pick the best matching pool. As I said, so some people, of course, will claim that this is extremely important. Some people will say, let's randomize it a bit and just stick to randomized version of this parent selection. So it doesn't matter too much if we do it in a deterministic way or totally random selection. But the survivor selection is extremely important, because this is the clue part. So I will repeat again. So in local search, we are just picking the best, and in Metropolis Hastings, we are randomly select whether the point is, even though the point could be better, we randomly select it. Okay. Right. So here a simple notation, because it's used in many papers and books. So by mu here we mean the number of parents or old individuals, and by lambda we denote the number of new individuals, or so-called offspring. And survivor selection is just replacement. All right, and we distinguish two kind of replacements. First, so-called age-based. So after some time, after some generations, some individuals die anyway, or fitness-based replacement. All right. So we just look at fitness function and we proceed. What we can use? The simplest approach, so-called a generational approach, and this is the age-based approach. So we generate the same number of new individuals as the number of old individuals, so lambda equals mu, and just we simply discard all parents, and we just look into new individuals. Where do we see this situation? For instance, in the estimation of distribution approach from previous lecture, so in some sense, we can say that we discard all parents. So we fit a distribution to the population, we generate new points, and we just select from these new points the best ones. All right. And the other approach is so-called FIFO approach. So first in, first out. We generate less new points than old ones. We add offspring to the FIFO queue, and we just remove head of the queue, or a couple of points from the queue. So this could be this approach. All right. So this is this age-based. So we know that they must die in some sense. Of course, you can think of much easier, much more straightforward, let's say, more like biological. So we can assume that some points they die in some sense. So we can, for instance, add to every single individual, we can add age, so the number of generations, and we can randomly sample according to the age. We can sample whether the point dies or survives or lives on. again, so this is very open, and please remember that these evolutionary algorithms, they try to take advantage or look at the reality, at biology, life sciences, and so on, and they try to mimic reality, right? So maybe some mechanisms are not represented so far. Maybe you can come up with new mechanisms. Maybe they will work better, right? The fitness-based replacements, so they are, I would say, I think, very common and commonly used because they are very close, I would say, to optimization algorithms or these sampling methods. So the best so the widely used replacements or replacement mechanisms, so they are, for instance, replace wars. So you just so-called genitors. So the worst lambda individuals are replaced by offspring. Closely related idea is elitism. So we from epoch to epoch we always keep a subset of best individuals, and they are always kept together with the offspring. So it's some percentage of old population. So this is to just keep track on the best solutions so far. Another mechanism is round robin tournaments. So we select some individual and compare it with Q individuals randomly selected, and we just again. So if it wins, it gets a point, and we just look at individuals and we see how many times they won. So by winning, again, we mean that the fitness value is higher. And we just pick new individuals with highest number of wins. This is again simple. Another selection, and this is very widely used, it's mu plus lambda selection. So this notation with brackets, it's taken from evolutionary strategies. And what this mu plus lambda, so what does it mean? It means that we generate an offspring, we take the old population, we take new solutions, and we merge them together, and we simply pick best new individuals, and they constitute a new population, right? So this is, again, if you think a bit about it, so this is in some sense just to keep track on best solutions so far. If some points are good, they were good, so we just keep them. And next is mu and lambda, right, in brackets. So we create lambda children from mu, such that lambda is larger than mu, and mu best children constitute a new population. So you see that we disregard parents and we just look at children. And of course, these are very important because this is, we are going to mutation. So these are extremely important mechanisms, and very often they will give you a good or bad solution in the end, or premature convergence or very slow convergence. There is no single, I would say, decision or consensus which is better. For some mutation and crossover operations, some of these selection mechanisms work better than others, but it is not clear. There are some maybe rule of thumbs, but this is not very clear. For instance, mu plus lambda is a rather safe option, but also not always. And now we move to the last point. So how to generate, right? So first we look into mutation operators. So a mutation is a function that takes an individual and produces another individual. So this is something like from one individual create only one. From one parent we create one child, right? And the transformation depends and highly depends on the representation. What does it mean? It means that if we have the genotype or the representation of an individual, it's binary, so in bits, integers, combinatorial, like discrete permutations, or continuous, or graphs, for instance, trees, we cannot so simply take one mutation and apply them to all of them, right? We need to implement it for very specific representation. And what we can use for bits. For bits, for instance, we can flip bits. What does it mean? It means that we can, for instance, generate a mask, binary mask, of the same size as our individual. We just sample, a vector according to Bernoulli distribution that you know already from previous lectures. And so it will be 0, 1 vector. And if the parameter theta, so the probability of selecting 1 is high, we'll flip a lot of bits. If it's 0, so we'll not flip so many bits. And how is the perturbation? So it's just we simply add our original individual represented by bits. This is denoted by x. We just add this this mask, binary mask. And then, of course, some values, if it was originally 0 and we add 1, it's fine. But if it was 1 and we add 1, it will result in number 2, right? So then we need to take modulo operator so that we end up with binary vector. And maybe we can look into that again very quickly, so to have this impression what we are talking about. So let's say that we have our original x is 0, 1, 1, 1, 0, 0. This is our x. This is, we select some mask. Let's say this is 0, 1, 0, 0, 1. We add these things together. So it's 0, 2, 1, 0, 1. We take modulo 2. What does it mean? If modulo its operator is defined that we just take in modulo 2, let's say A. If it's 0, it's 0. If it's 1, it returns 1. If it's 2, it returns 0, right? So now we look, we have 0, it's 0, it's 2, 0, 1, 1, 0, 1. All right? So we see that actually, because these two were the same, so we just flip this bit, all right? And because here was 0, and we added 1, so we flip this bit. So basically from the original vector, we flipped 2 bits. Right, I hope that everything is clear. All right. Let's continue. Another possible perturbation is XOR perturbation. So we again sample a mask, and we just this binary mask, and we just apply this logic operator XOR. Maybe again, let's take a look how it works. So we have x 0, 1, 0, 1, and XOR operator. Maybe let's define it. We have A and B, and this is the result. So if we have 0, 0, 0, if we have 1, 0, it's 1, yes, I think. 0. So XOR operator tells us where is the difference between bits, all right? So this is how it is defined. So now if we have a mask that is, let's say 1, 0, 0, 1. So this is what we generated. Okay. So it's so this is what we generated from Bernoulli. So then we will have so then of course we'll have XOR operator, pardon. So then here we have 1, here we have different, so it's 1. This is the same, it's 0. These are the same, it's 0. So you see, by applying XOR, we can change this object into something new. And they, for instance, we changed here value and we changed value here. This remained the same, right? So we changed original bits here and here. All right. All right. So these are possibilities for binary representations. Now for integers, first is random resetting. What does it mean? We sample a mask, we sample new integers, so a vector of integers, and then we just element-wise we multiply. So this mask is which positions we will zero out, right? And now we will just, in these places that we decide, oh, we zero out here, so we'll just add an integer in this place, a new integer. Maybe let's quickly show how it could be. So let's say that I have x. I have x, 5 minus 6, 7. I have y, 8, 11, minus 2. I sample a mask. Or maybe actually to keep it like this. All right. What does it mean? It means that only this here we will change, because now we multiply m times x. It's 5 minus 6, 0. Now we take the opposite. So we see that it's 0, 0, minus 2. And now we add these two together, maybe like this. Element-wise, so we have 5 minus 6 minus 2. So we see that original we change this the last dimension. Right. Another thing is actually very simple. Another possibility, this so-called creep mutation, is that we again sample a mask, but now we also sample integers symmetric around 0. Right. So now this mask will determine where I want to add a value, and this added value will be sampled from a distribution around 0. Next mutation is for continuous representations, and this for continuous representations we have, I think, the largest number of possible mutations, because we can use really different things. So the simplest one is random perturbation. So we just pick a distribution for probability distributions like Gaussian, Cauchy, uniform, whatever. We just sample value from this distribution and we just add it to X. So this is in Metropolis castings, for instance, we showed a Gaussian, but it could be any other. For evolutionary algorithms, we can even make it that we want to sample from some point. This is like that. A very interesting possibility is so-called self-adaptive mutation. So of course, if we sample from Gaussian with large variance, so then of course over time it will be like it will it will jump away from good maybe solutions, and we don't want that. So we want to maybe also modify the variance over time. So we will just modify the variance according to some scheme. It could be like smaller and smaller over time, and we can do it in this way that it's presented here in this slide. So maybe one remark. So the last perturb. So we first sample standard Gaussian. We multiply it with variance, or sorry, standard deviation, that is, smaller and smaller over time, and we add it to previous point. A different approach to self-adaptive mutation is that we just estimate diagonal covariance matrix from our population. All right. So there are possible known estimators and so on. And so this is very simple. The drawback of that is that, of course, for highly dimensional cases, calculating the covariance matrix could be very difficult. And another approach that is extremely interesting is that we sample two individuals from our population, and then we calculate what is the difference between them. We multiply it by some constant value a, and we add this difference to our old parent, let's say. And why this is interesting? Actually, let's take a look at it graphically. We will look at 2D problem. So let's say that we have a Gaussian. So Gaussian more or less samples. Oh, it's actually very bad. Oh, sorry. So my drawing skills on this device are not the best ever. So right. So let's say that this is a Gaussian. Variance 0, mean 0, and some variance. Okay. But now let's say that we have points. We have our population x1, x2, x3, x4. And now let's say that we calculate differences. So how many of possible pairs do we have, right? So we have one with 2, one with oh, this is 3. One with 3, one with 4, and so on. But also one with 2, it's also 2 and 1. This is another pair, right? So now we will have, in general, let's say that we have, of course, we have more of these points. So now we will have these differences, and we can, let's say in 2D, we can denote it as maybe let's change a color. We can denote it as a point. So let's say that we have. We have 1 point. This is the difference, right? So this is the difference between some points. So another point, another point, another point, another. And if we have pretty large population size, we'll have quite a lot of these points. Actually, this will grow very quickly with the number of population size. And each point, right? Each point corresponds to xi minus xj. And now you can think of this perturbation let's say we will denote it as our perturbation, that it follows from some distribution, right? So in this case, and in general we have x plus delta. This is our new point. So now in this case here, so this is how we do it. In this case, delta follows from Gaussian. But in this case, delta follows from this weird distribution that I don't know even how to do it. So how to define it, because this is a set of points. So we sample from this, so we for instance pick this point. For another point, another interval, we'll pick this one, and so on, so on. But also, if for every point we can sample one of these differences, all right? So this is an interesting point of view perspective on how to think of differential evolution. So in fact, it can be also very adaptive, because over time, these sets of points over here, they will be sampled not like this, but maybe they will be from some region like this, so smaller and smaller, because points converge, and then from this. So this is self-adaptive already. But if we use Gaussian and we define this variance, so it will be the same over time. So then, of course, it could be very bad for our convergence, and we need this self-adaptation. Okay. All right. All right. Okay. So differential mutation is a very interesting concept, and it is only heuristic, but in my opinion, it has very nice properties, and it could be used more often actually. All right. What about permutations? So for permutations, we can do swap. So for instance, we select two positions and we just simply swap them. And okay, what are permutations? So for instance, we have this traveling salesman problem, and we have that we need to we have three cities. So first we visit third one, then we visit first one, then we visit second one. Okay, we have three cities, and how we visit them. So for instance, 3, 1, and 2. This is how we visit them. If we make a swap, for instance, we swap them like this, and then our solution is now, so we go from 1 to 3, from 3 to 2, okay, and so on. Insert. So we randomly select two positions and move the one on the right next to the one that we selected with the second one on the left, right? So we pick a point and just swap the neighbors next to each other with positions. Scramble is a generalization of insert. We just pick some subset of positions and we just, swap. We just swap a couple of positions at once. And inverse is like scramble, but we instead of randomly sampling, we just invert values. About trees. So with trees, it's a little bit more complicated, but for instance, we can change one node or sub node with some value, or we can remove something or add something, and so on. Okay, so the beautiful thing about evolutionary algorithms is that you are really not constrained on operations you want to use. If you have a hunch that something will work, you can always check it, you can always implement it, and you can analyze it, all right? The downside is that it could be very non-theoretical, in the sense that we don't have some maybe theoretical mathematical grounds for calculating convergence or something like that. All right, so these are mutations, and they are really nice. In my opinion, they are very easy also to follow, because this is something like this mutation I like to call perturbation, right? So it's something like you add something, you add some noise or some smart noise, like in differential mutation. But also you can actually change your points by changing 2 points together, right? So what does it mean? So recombination, or sometimes called crossover, is a function such that it takes two individuals and creates a one new one, right? And again, it is different for different representations. So like before, binary, integers, combinatorial, continuous, and graphs. And the most commonly used crossover is so-called endpoint crossover. What does it mean? Let's say that on the left and on top we have two parents on the left, gray one and white one. We just select one point and then we will replace the second part. Will go from gray to the white one and white one to the gray one. Okay, so we see that actually we created two children, right? So one may be inconsistency. On previous slide I said that from two parents we create one, but actually we just create here two ones. In many cases actually we create two new. 2-point crossover. So we select 2 points and we replace one part with each other. Uniform crossover. So we just select which indices we want to swap between two parents. All right. I hope that these figures are self-explanatory. Now, what about arithmetics or continuous recombination, right? So the main idea is to take two parents, select points, so this is simple arithmetic, and just interpolate between these points, okay, with some alpha value. So on the right top we see that we have simply alpha set to 0.5, so it's just average, and we can just calculate average of these two parts. Single arithmetic. So this was simple arithmetic. Single arithmetic is that we just take one single position and we calculate, for instance, average, right? And whole arithmetic is that we just take two parents and we calculate average or this interpolation of these two, and then we get this one single new individual. Okay. And also to maybe defend in some sense this mistake that I made, that we generate this new individual, because we can actually calculate, for instance, crossover from two parents, but then pick only one of them. Okay. But there is nothing against to pick both of them. Of them, I mean new individuals. What about trees? So we can, for instance, swap subtrees. This is a very common technique. And then, of course, we get totally two different trees. Of course, downside is that we sometimes need to keep track of of these new generations, whether they make sense or not. And that's it. So to summarize, to sum this lecture, I would say the beauty of evolutionary algorithms is that they are very general, and we have very general description or prescription how to formulate new algorithms, and then by looking at specific blocks we can create a lot of different algorithms. Moreover, we can focus on some specific operations, and we can formulate totally new algorithm or totally new for instance mutation, and then you can now play with different selection mechanisms. You can check whether this is better than that and so on. So there are multiple different options, and they could give you, some combinations could give you better results than others. Personally, my perspective is that this is really nice because this is something like it's open for new ideas. There are little constraints, and you can really maybe look into reality or life outside the window and maybe think, okay, so bees behave in this way, and we have so-called B algorithms, B-based or something like that, the swarm optimization in general, and so on. So this gives a lot of opportunities to formulate new algorithms. And I hope that after this lecture you see this chance, and that you will also go a little bit wild with the next assignment. All right, thank you very much. Take care, guys.